So the last general construction we'll see in this course is that of a quotient topology. From a geometric point of view, maybe the most important. I mean, the products and so on tend to give rather special spaces, but interesting ones you see: Mobius band, manifolds, cell complexes. All of them are typically from the quotient topology. So suppose we have X as a topological space, as usual. And then suppose let tilde be an equivalence relation. So this is a symmetric, transitive and reflexive relation on tilde. Then, as it's well known, you get a partition as sets. Okay, we have a quotient set. So let me call it X bar, which is the set of equivalence classes of elements in X. There is a quotient set. So cyclic groups are constructed this way. And what we want to do is we want to make this a space, as a topological space. Okay, so quotient topology on X bar this time, instead of defining what it is, as is more often done, we'll just define and then showing its properties. Let's try to do it the other way for a change. Let's define it to be the final topology induced by so we have quotient set. We also have quotient map X bar, which will take each element to its equivalence class. Okay, so final topology induced by Q, mapping X to X bar. That is the finest topology on X bar such that Q is continuous. Okay, we can figure out what it is, we will, and it's easy to give a direct description, but as an example of figuring out how finite or initial or final topologies, I've defined it in this way now here. So what does this mean? Okay, so if Q is continuous, let's see what that condition means. If and only if. So V contained in X bar open implies Q inverse of V open. Okay. So if omega is the final topology, it must be that any set in omega, V belongs to omega, implies that Q inverse of V open. This doesn't even use the fact that it's final topology, just that it's a topology such that Q is continuous. That is, omega is contained in, let me call it omega naught, which by definition is the set of elements in X bar such that Q inverse of V is open. And omega is the largest such topology. So what is the issue here? A priori omega naught may not be a topology. So if I just have a bunch of functions and declare they are continuous, all with a fixed target, then any set in that topology must have inverse images of all the sets of that set under all the functions as open. Here we have only one function, and a priori this will not be closed under intersection and union. I mean finite intersection and arbitrary union. Okay, but in this case, in fact, so proposition omega naught is a topology. Hence, omega is the largest topology that is contained in omega naught, which is of course omega naught itself. Okay. So in general, if it's an initial topology, you may have to increase the size and if it's a final topology, you may have to decrease the size from the given open sets, from the sets we can deduce to be open, or in the initial topology. In the final case topology, we can deduce any open set is one of some collection. We may have to cut down the collection. But here we don't, because this is a topology. I'm not going to verify all the properties. So of course, first of all, if I have a collection Vi contained in X bar open, so V alpha open for all alpha implies that Q inverse of V alpha open for all alpha in some collection A, again A, which implies that the union of alpha in A of V alpha. So if I look at Q inverse of this is union alpha in A V alpha of Q inverse of, sorry, that's not V alpha, union of this of Q inverse of V alpha. But that is open for all alpha, which is open. And hence, so Q inverse of this is open, hence union alpha in A, V alpha is open. And I'm just going to say rest similar, because again, because finite inverse images behave well, finite intersections of inverse images are inverse images of finite intersections, and empty space and full space have similar properties. So we have the case. Okay, so now we know what a quotient topology is. Okay. So thus it's worth writing it, because you'll use this topology on X bar, or maybe I'll emphasize quotient topology on X bar is just a set of all Q inverse of V contained in X bar, sorry, Q inverse, I'm sorry, the other way around. So it's the set of all V contained in X bar such that Q inverse of V, which is now a subset of X, is open. So quotient topology on this is this. This is nice that we know the explicit set, but it's better to see it in terms of functions. And here what we have is the following theorem. Okay, so suppose we have another space Y. Let Y be a topological space. And the way I'll state it here is, first of all, let's take F bar from X bar to Y a function. And let's say F is Q composed with, compositions go the other way. F bar composed with Q. This will map X to Y. Okay, so we have a quotient and we have a function. So we have X here, and we have a quotient which is sort of becoming smaller. You can think of vertical lines as being equivalent, so it's become thinner. I have Y here, and then I have F bar. This is my Q, and this is my F. And what we have here is the fact that if I look at F bar composed, and F is this is the relation at functional level, then F bar is continuous if and only if F is continuous. Okay, so let's see. This is actually rather easy to prove, but I called it a theorem because it's a significant result, and we'll see 2-3 other ways of interpreting and using this. Okay, so where are we? We have F bar and we have F. We want to show, so F bar is continuous, is equivalent to, for all V contained in Y open, F bar inverse of V is open. But what does F bar inverse of V being open means? So equivalent to for all V in Y open, F bar inverse of V is open if and only if Q inverse of F bar inverse of V is open. Okay, but Q inverse of F bar inverse is actually Q composed with F inverse. So for all V in Y, open. I'm just writing it in a slightly verbose way for once. This is open, but this is F. Yeah, so for all V in Y, open, we have F inverse of V is open. And the last one is obviously, so equivalent to F is continuous. So if I have a map on the quotient as a set, it is continuous if and only if the original map or the map on the original space is continuous. Okay. So in interpretation, so consequence is the following, and this is the way we'll usually use it. We'll use it where F is given to be continuous. Okay, so suppose F from X to Y is continuous. And we have tilde as an equivalence relation. So X bar is X over tilde, of course, as usual. So suppose this is continuous and we want a map on the quotient. Now you got a map on the quotient if two elements which are equivalent go to the same element. That is just at a set theoretic level, because you have to have a map on the equivalence class. And x1 is equivalent to x2 implies f of x1 equals f of x2. Just to clarify, these are elements in Y. So these are two elements. If they, and tilde is an equivalence relation such that, and well, so this is the data, and we have the function having the property that equivalent elements go to the same element in Y. Then we have a continuous function. Where was so we have a continuous function f bar from x bar, which is let me write it below, equals x over tilde to y, such that f is actually q f bar composed with q. So we have an induced function on the quotient, and the induced function on the exactly when equivalent elements go to equivalent elements. Okay, so sorry, equal elements in Y. So just a quick comment about the proof. We simply define f bar of the equivalence class of x is just f at x, and see, this is well defined. We'll see an even more usable version of this, little less to check in a moment, but let's just look at this again. So the point is that if I have just a function at the level of sets, you get a function on equivalence classes, provided whenever two elements are equivalent, they have the same image. And the content of this, which follows from the theorem above, is if your original function was actually a continuous map, then on the quotient also we get a continuous map. So this lets us define maps on quotients. Indeed, this is how we will use quotients a lot. Okay, so also a variant of this, if tilde is generated by some r contained in x cross x. So r is some relation and tilde is I should clarify what is the equivalence relation generated by this. This means we are told certain number of elements are related, certain pairs of elements are related, maybe an empty set of pairs, maybe lots of them, and we can always look at a corresponding equivalence relation, which is that symmetric transitive reflexive closure of these. That is, look at all equivalence relations containing R and intersect them, and that gives you a tilde, which is, suppose this is generated by tilde, okay, and f maps x to y is a continuous map So we have such a continuous map such that if I have any pair x1, x2 in R which are related, then f of x1 equals f of x2. So we'll see an example. Sometimes there's a much smaller number of things for which we have to check. Okay, that f of x1 equal to f of x2. Then f induces f bar from x bar to y such that f bar, if I compose it with q, I get f itself. Okay, so the idea is the following. We have to pass from a relation to the equivalence relation generated by this. Well, just note, given f mapping x to y, okay, so the relation f of x1 equals f of x2 is an equivalence relation. So given a function, having the same image is an equivalence relation. Just because equality is an equivalence relation. In fact, if your image is being related by an equivalence relation also gives you an equivalence relation. Just notice f of x is f of x, of course, it's reflexive. This is symmetric. And if f of x1 is f of x2 and f of x2 is f of x3, then f of x1 is f of x2. This is an equivalence relation, and by hypothesis, I'll give this a name. Let's call this some tilde f or something like that. By hypothesis, R is contained in tilde f. That is, any two elements that are related in R are related by this. But so hence tilde is contained in tilde f. Because the equivalence relation generated is the smallest equivalence relation. This is an equivalence relation containing R. So it's contained in tilde f. That is now, if we have x1 is equivalent to x2, then f of x1 equals f of x2. Okay, now use the previous result. So we got a free upgrade and a free up from just any relation to an equivalence relation. From a given any relation, and you're looking at the equivalence relation generated by that, we only have to check for those which are equivalent in the defining set R. Symmetric and transitive closure is automatic. That is because equality of function values has symmetric and transitive is closed under symmetry and transitivity, and is also reflexive. So this is the most usable form. So we have a quotient topology which will let us, we will see next, do things like take an interval, identify the ends, make it a circle. This is what we'll start with, but since I was telling abstractly, so really here we have only one relation. 0 is equivalent to 1. Everything else is kind of automatic. Each point is equivalent to itself and so on. So you're looking at reflexive transitive closure of this. It's to have an induced function on the reflexive transitive closure. It's enough to check that the value at 0 is equal to the value at 1. So there could be a drastically smaller set that we have to check the action on. This part is just, this passage, last part is just pure sets, relations, functions. It has now not to do with topology. So what had to do with topology is that continuity is inherited automatically.